Hello, and welcome to part 2 of worksheet 10. This is on graphs. So graphs, as you are probably familiar at this point, are a generalization of the tree or linked list data structure. They can be pointing forward or backward, any way you want. They're a very general data structure. We'll see them in a lot of places all over computer science. And yeah, we're starting to talk about them now. So this first question here is mostly going to help us get familiar with some of the mechanical aspects of graphs in the same way, just with heaps. A minute ago, we did all of the basic like add and remove operations. Here, we're going to do some of the kind of core representation and traversal operations of graphs in this problem. So the first part is we want to write the above graph as an adjacency matrix and as an adjacency list. So I have created here, let's get this all in frame. I have created here a little adjacency matrix and list, so you don't have to watch me draw it out. And we're basically just going to put things into here based off the graph. So the way that an adjacency matrix works is it's basically a 2D array, which I have here represented by this grid. And on one, and basically what we're going to do is every element is either going to have a 0 or a 1. A 0 means false, a 1 means true. So basically, if there exists an edge between one side and another side of the graph, we're going to put a 1 in the corresponding box in our adjacency matrix. Also keep in mind that this axis is going to represent start, and this is going to represent end. So we're going to say, okay, if there is an edge between, say, A and A, it starts at A and it ends at A, we're going to put 1. Or if there's one that starts at A and ends at B, we're going to put a 1 there, right? Okay, so now we can just go through and fill this out. So this is basically all we have to do. So let's just go node by node. So A we see has edges to both B and D. So I'm going to say there's an edge from A to B, there's an edge from A to D. So I'll put those as 1s. Everything else will be a 0. Now let's look at B. B has an edge to C and nothing else. B has some incoming edges from other places, but right now I'm just looking at outgoing edges only because I'm kind of going from start to finish. So we say there's an edge from B to C, and then there are no other edges coming out of B. Let's look at C. C has an edge to F, so we can just put that there. No other edges. D has an edge to E, and it has an edge to F, and it has an edge to B. So we're going to put B, E, F, just like that. Everything else is a non-edge. E has an edge to F and nothing else. F notice has no outgoing edges at all, so everything will be 0 in the F row. And then G has one edge, it goes to F, so put 1 there. And then everything else will be 0s. So this is everything. This is an exhaustive list of all the edges that could possibly exist in our graph, and everyone that has a 1 indicates we have a start and finish to that. So that's what the adjacency matrix would look like. Let's look at the adjacency list now. The adjacency list is going to be a little bit easier because we're not going to worry about all of these 0s, right? We're only going to write an edge if it explicitly exists. So this basically represents the start point. And so, for example, what we're going to do is we're going to say, okay, what edges come out of A? Well, we have an edge from A to B and an edge from A to D. So we're going to have like a list here of of B and D. In other words, we have 2 edges here that are being represented. They both start at A, and one goes to B and one goes to D. Then we can continue down the list. B has an edge to C. C has an edge to F. D has an edge to B. It has an edge to E. It has an edge to F. Just like that. E has an edge to F. F has no edges, so I'm going to represent that with like an empty list like this. And then G has an edge to F, just like that. Okay, that's all we're going to have to do. You can see it's a little less work to actually write it out on paper. And hopefully you can see, though, how these both represent the same thing, basically. They both represent what edges we have. So there are some pros and cons to both. The adjacency matrix is really nice because it's very easy for us to just look up is there an edge between D and, C? No, there's not, because you can just go straight here. It's a constant time operation to look it up, no big deal. Whereas if we wanted to do that with the adjacency list, you would have to traverse this entire list right here and see if there's a C. So you have a linear time based on the length of the list, which is at most the number of edges or the number of vertices, to figure out if an edge does exist, or you have a constant time. You can speed this up a bit, I guess, by sorting it, blah, 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 blah. But generally speaking, this one is going to be faster. But of course, the disadvantage is that, as you can see right here, the adjacency matrix is going to take up more space, especially as this graph gets really, really big. This is an n squared thing because we have a 2D grid, whereas the adjacency list is only going to get as big as many edges we have in the graph. So if you imagine we have like a huge graph, but there aren't a lot of edges in it, this is going to be a far more efficient representation than what we're going to end up with this, because most of this, right, even with this relatively small graph, you see that most of it's populated by zeros, and that's just a lot of memory to waste. Okay, that's some of the basic stuff there. Now, the part that you are probably here for, and the more tricky and kind of algorithmic section here, is a traversal of this graph. How are we going to actually do a traversal? So we need to do 3 of them. We need to do a DFS pre-order, we need to do a DFS post-order, and we need to do a BFS traversal. Okay, so you're probably familiar with all of the terms. We talked about them when we were using tree. When we were doing trees, BFS you may have heard referred to as a level order traversal, but the more general term for it is BFS traversal. So DFS pre-order and post-order, what do they look like in terms of graphs? So if you remember when we were doing binary trees, a DFS pre-order was you visit the node, then you go to the left child, then you go to the right child, right? Now in a general graph, we don't have a left child and a right child. We just have children. They don't have an explicit ordering to them. So we're going to generalize that process to basically just visit and then children, right? And similarly, post-order is going to be in the original BST, we did left child, then right child, then visit. That gave us post-order. Now it's going to just be add all children or visit all children and then visit yourself, basically, is how it's going to work. Hopefully you can see how these generalize from the basic principles that we did with a BST. Notice there's no such thing as a DFS in-order traversal. And one reason for that is that a in-order traversal in a BST is kind of predicated on the fact that you have a left and a right, right? Like you have a left child, then you can visit, then you go to the right child. When you just have general children that aren't ordered in any structure like that, you can't really define a notion of a left and right. Different graphs are going to have different numbers of children, so it doesn't really work to define an in-order traversal, or at least if you do, you have to be really, really specific in the criteria. So that's why we don't have that. DFS is going to be just as you would expect before. It's going to be basically, it will be a visit and then add children, but it's going to be a little different in that we are going to kind of radiate out from a core point as opposed to DFS where we go deep first. Okay, that's some of the conceptual stuff. Let's look at how you would actually run this algorithm on this graph, starting with the DFS preorder. So we need 2 things here. We need to have a fringe and we need to have a scene. So the fringe is basically going to be a data structure. In the case of DFS, it's going to be a stack. And this basically is our, it's kind of our queue. We don't call it a queue because a queue is a different data structure entirely, right? As you're probably familiar with, but it's a queue meaning that the things that we are going to traverse are waiting here, basically. So this fringe is going to be implemented via stack for DFS traversals in general. Stack is always for DFS. And then we have this other set, which is scene. It's just basically every time that we, not that we visit a node, but every time that we add its children, we're going to add it to the scene set. This is going to help us from adding the same thing multiple times over. And we'll hopefully see why it's important, especially once we do like a DFS post order. Okay, so we're going to start at node A, and let's see how we do this. Okay, so the first piece of setup is we're going to add A to the fringe, right? You always have to add your starting node to the fringe on its own. Then from here, we're ready to actually start the algorithm. Okay, so what are we going to do? First thing we're going to do is, remember, we're doing a DFS preorder, so we're going to visit, and then we are going to add our children after we visit. So the first thing we're going to do is we're going to pop A off the stack. A is the only thing in the stack, so it's the thing that's going to get popped off, right? Which means we're going to add it here, this little thing under the DFS preorder actually represents the order we're visiting the nodes in. I didn't actually specify, but this is the order. So A is the first thing visited, popped off the fringe. And then what we are going to do is we are going to add its children, right? So we are going to say that it has been seen once we've added its children. And what are its children? A has 2, it is B, and it is D are its children. Okay, so one thing to note here that's very important, and a lot of people were confused about this in a previous lab, is we want to tie break alphabetically, right? So we want to visit B before we visit D, right? And if you just kind of try to do a little bit of DFS in your head, you'll see, well, we're going to start at A and then we have to go somewhere. We want to go to D before we go to B. That means, though, that since we are using a stack, right, whatever is on top of the stack, the last element of the stack is the thing we're going to visit next. It's the thing we're going to pop off. So if we want to visit them in children in the order BD, we have to add them in the order DB. So this is just a general principle. Whenever you're adding to a stack in a DFS traversal of a graph, if you have a tie-breaking scheme, you have to add things in reverse order that you want them to be tie-broken, right? Just because if you look at this fringe, the next thing that is going to be popped off is B, not D. Okay, that was a point of confusion that a lot of people had. And it's also even more confusing because when we do BFS, you don't have to do this. So try to keep in mind, DFS, you have to add them in backwards. Okay, anyway, so we'll do that. And we've added A to our scene set. Okay, great. So we're all done with that. Next thing we're going to do is we're going to pop the next thing off the fringe. What is the next thing? Well, we are popping off B, right? Why are we popping off B and not D? Because it is a fringe. So we're always, or because it's a stack, we're always popping the last thing off. We're popping off the most recent thing that was put in, which in this case is B. Okay, so we're on B now. So we're visiting B. We can add that. And now we need to add B's children. So we're going to add it to the scene set. Does B have any children? It does. It has C. So we're going to add C to our stack. It only has one child, so there's no need to worry about tie breaking. And then we're going to move on. Okay, now we're going to pop off the next thing, which is just C. So we are going to visit C. And now we are going to add it to our scene set because we're going to start adding its children. What children does it have? It just has F. It only has one child. No worries about tie breaking or anything like that. So let's add F to the stack. Now we pop off F. Visit F. Add F to our scene set because now we're visiting or we're looking at its children. Does F have any children? No, it does not. So it doesn't have any children. That means we're going to go back to the fringe and pop off the next thing. Notice what is the next thing? It is D, right? We've finished with all of the children of B, so now we're getting back around to D. So now we are looking at D. We're going to visit it. And now here is where having this scene set is nice. So we add something to the scene set, right, when we visited its children already. And there's no need for us to visit children multiple times in this traversal. So what we're going to do is we're going to add all of these children, but we're only going to add the ones that have not been seen already, basically, right? Because we don't want to see it again. Okay, so let's look at this. So we have 3 children. We have B, F, and E. B has already been seen. F has already been seen, so you don't need to add these children. So actually, all we're going to do is add E, right? Let's add D to our scene set because we just looked at it. Great. Next, we pop off E from the stack. So that goes here. And then we add all of E's unseen children. E has no unseen children, right? Because it only has F. And F has already been seen, so we don't add any children. We're going to add E to our scene set. We go to pop off the next thing from the stack, but we see, oh, the stack is now empty, and then we're done with our traversal. So the correct order is going to be A, B, C, F, D, E. Notice that we never visited G. The reason we never visited G is because we always add children, right? So you can see if we start at A, there's no way to get to G from A. So we would never add it to our fringe, hence we would never pop it off. There are multiple things you could do to fix this problem. You could, first of all, one thing you could do is you could, after you finish the run of A that we just did, you could look at the graph and say, hey, is there anything that's been unseen? Oh, G is unseen, then you just do G, or you could just not do it. That's for you to decide, but this is the main traversal order. Okay, that's how you do a pre-order. Next, we're going to move on, and much like Björk's second album, we're going to post. So we're going to do a DFS post order. So DFS post order is again going to be pretty much the same process overall, but now we're going to add the children first, and then we're going to visit them. Okay, so just as before, we're going to kind of get everything ready by starting with A, right? So we're going to put A on our fringe, and now what we're going to do is we are going to add A's children, right? We're not going to pop A off the fringe yet. We're not going to visit it. We're just going to add its children. So we're going to add it to the scene because we add something in the scene when we've added its children, and we add the children of A, which are again D and B. Again, we want to break ties alphabetically, so we have to put the D in first before we put B in. Okay. Great. So we've done that. The next thing we do is we are going to B, because it is the most recent thing in our fringe, in our stack. We're not going to pop it off. We're going to see, okay, B has not been visited, basically. So we're going to visit it first, right? This is why it's really nice, or sorry, not visit it. We're going to add its children. This is why it's really nice to have the scene set, because what you can do is when you look at a node like B, you can say, okay, is B in the scene set? If it is not in the scene set, that means that we have not added its children first, so we have to add its children before we visit it. If it is in the scene set, which we will see later, then we have added its children already, and then it's time to pop it off, right? So that's why it's really nice to have these two sets. Okay, anyway, so we get fringe from the top of the stack. We don't pop it because it's not in scene. So now we're going to add its children. We will add it to scene, and we will add its children. It only has the child C, so we will put that right on there. Okay, now we look at the top of the fringe again. C. Okay, C is not in scene, so we are going to put it in scene. We're going to add its children. We just add F. We look at F. We say, okay, F. F is not in scene, so we're going to put in scene, add its children. F has no children, so we don't have anything to add. Then we're going to go to the next thing on stack. Well, F is the next thing on the stack, right? Because we didn't add any children. So what we're going to do is we're going to say, okay, is F in scene? F is in scene, and since it is in scene, we are going to pop it off, visit it. That is our first node we're going to visit, F, and then we're going to move on, right? So that's the big difference. If you haven't seen it before, add its children. If you haven't seen it before, that means you must have added its children already, otherwise it wouldn't be in scene, and it's time to pop it off. Continuing along, we go to the next thing at the end of the fringe, which is C. We see that C has been seen already, so we're going to pop it off, and we're going to add it to our post order traversal. Great, now we go to B. B also has already been seen, so we're going to do that, pop it off. Okay, now we go to D. D has not been seen yet, right? Notice D is not in the scene list, or the scene set down here, so we're going to add it to scene, and we're going to add its children. We are, again, only going to add its children that we have not already seen, because if we've already seen them, we don't need to. In that case, or that means that we only add E in this case, because F and B have already been visited. No need to add them again. And then we continue on. So now E is now the thing that is at the end of our stack. So pop off E. Why are we popping off E? Because we added its children first already. Sorry, I forgot to do that first. We added its children, but it doesn't have any new children because F has already been seen. So then we go back and we pop it off. Okay, and now we pop the next thing off. D is now in the scene set. So we can just pop it off, look at it, and we go back, and A is in the scene set. So we just pop it off and look at it, and we're done. It's really ugly looking A. Okay, great. So this is how you do post order. This is the more complex one. This is the one that's more involved. It's definitely harder to do in your head. So I'd recommend trying it out on paper a few times and trying to get it down first. But there's a lot of logical things here we can look at too. So remember, we only visit a node once we visit all its children, which means necessarily the first node in a graph like this that we're going to visit is the one that has no children, or no children that we haven't already seen, which is why F in this case is the first one we visit. Also notice again that A is the last thing to visit, and that is always the case in a post-order traversal, that the node you start on will be the last you visit, because in order to visit it, you need to have visited all its children. If it's the node you start at, that means you have to basically have completed everything before you visit it. Okay, that's the hardest one. Great, now we're going on to BFS. BFS is different because instead of using a stack, BFS is going to use a queue, or a queueway, as they say. It's going to use a queue, but otherwise the process is basically going to be the same as DFS preorder. Just the order is going to change because of the data structure we're using. Okay, and let's just do a quick example of that. Okay, so we're going to start with A in our fringe, and then we are going to visit it. So we're going to pop it off, right? Because we visit, then we add the children, then we are going to add the children. So we will add it to the scene set, and then we will add the children, B and D. So notice in this case, you do not have to add the children in reverse order. That's because in the stack, we were always taking the thing at the end of the stack. We were moving kind of right to left in terms of elements we were popping off. In a queue, we're going to be moving left to right. So in this case, the tie breaking is easier to handle because you don't have to invert the order. So that's just a big note that differs from DFS. Anyway, so we add B and D in that order. And now we are going to visit B. So we're going to pop B off. We're going to visit it. We're going to add its scene, whoops, and add its unseen children, which is just C. So it's going to add C. Great, move on. D. We're going to pop D. Oops, we're going to pop D, add it to our order. Then we're going to add it to scene. We're going to add its unseen children, which are going to be E and F. Right, in that order. And then we're going to continue on. So then we're going to pop C. We're going to see it. We're going to add its unseen children. It doesn't have any unseen children because F has already been in the queue. You could add F if you want. You also don't have to. This is another subtle point here. So notice that F is already in the queue, but the criteria I was going on before said we add children if they're not seen, and F technically hasn't been seen. So you can add it into the queue twice if you want, or you could just not add it at all. It doesn't matter because this F is going to get popped first. And once this F is popped, you're not going to pop this one. So you might end up with something extra in the queue. You might not. It doesn't matter. I'm just not going to add it because we've already added it to the queue. Anyway, okay, so we just did C. Then we are going to move on to E. We're going to visit it. Here's E. Add it to scene, add its children. F, again, we've already seen F, so we're not going to add it. Then we're just going to move on to F. Pop it, add its children. It doesn't have any more children. And then we're done right there. So we have A, B, D, C, E, F for our BFS traversal. Of course, another way to look at the BFS is it just radiates out from a source. So if you kind of look at everything that is 0 nodes away from A, it's just A. If you look at everything that is 1 node away from A, it's this. If you look at everything that are 2 nodes away, it is this. And what you'll notice is that these things, these layers, everything that's 0 nodes, 1 node, and 2 node away, are the order of the BFS traversal, just sorted alphabetically, right? A, B, D, and then we have C, E, F down there. So that's another way to look at it conceptually. If you want to try to do it in your head, probably safer to do it on paper, but it's a way to look at it conceptually. Anyway, so that's how you do these basic traversals. And feel free to join me on the final part, which are some graph conceptual questions.